Stars begin their lives within vast cosmic clouds known as nebulae. These enormous structures consist of gas, primarily hydrogen and helium, along with dust particles. When regions within these nebulae become dense enough, they begin to collapse under their own gravitational pull. As the material falls inward, conservation of angular momentum causes the cloud to spin faster, much like an ice skater pulling in their arms. As the cloud contracts, the material at the center forms a protostar. The gravitational energy of the falling material is converted into heat, causing the core temperature to rise dramatically. When the core temperature reaches approximately 10 million degrees Kelvin, nuclear fusion ignites. In this process, hydrogen nuclei combine to form helium, releasing an enormous amount of energy. This is the defining moment when our protostar officially becomes a star. With fusion established, the outward pressure from the energy released balances the inward pull of gravity. The star reaches equilibrium and joins the main sequence, the stable phase of a star's life when it continuously fuses hydrogen into helium. The lifespan of a star depends primarily on its mass. Massive blue stars burn their fuel rapidly and may live only a few million years. Medium-sized stars like our Sun have lifespans of approximately 10 billion years. Small red dwarf stars burn fuel so slowly that they can shine for trillions of years. And so from the dust and gas of interstellar clouds, stars are born through gravity, heat, and nuclear fusion. These cosmic furnaces will continue to shine for millions or billions of years, their lifespans dictated by their mass. The leading theory for the moon's formation is known as the giant impact hypothesis. About 4.5 billion years ago, when Earth was still forming, a Mars-sized object called Theia existed in our solar system. This massive body was on a collision course with our young planet. Theia collided with Earth in a massive impact that changed our planet forever. This collision ejected a large amount of Earth's mantle and some of Theia's material into orbit around our planet. Over time, this debris gradually coalesced due to gravity, forming our moon. This hypothesis explains why the moon's composition is similar to Earth's mantle, and why the moon has a much smaller iron core compared to Earth. The moon initially formed much closer to Earth than it is today. Over billions of years, it has been gradually moving away at about 3.8 centimeters per year. The giant impact hypothesis remains the most widely accepted explanation for how our moon formed. Stars go through fascinating life cycles that vary depending on their mass. Main sequence stars, like our Sun, spend most of their lives fusing hydrogen into helium in their cores. When a star depletes its hydrogen fuel, it begins to expand into a red giant as it starts fusing helium. The star expands dramatically, becoming much larger and cooler on the surface, appearing red. After the red giant phase, stars follow different paths depending on their mass. Let's look at what happens to small and medium-sized stars first. Small to medium-sized stars shed their outer layers, forming beautiful planetary nebulae. The core remains as a white dwarf, extremely dense and hot, but gradually cooling over billions of years. Now let's examine the more dramatic fate of massive stars. Massive stars evolve into supergiants, eventually developing a layered structure with different elements fusing in each shell. When fusion can no longer support the star against gravity, the core collapses, triggering a spectacular supernova explosion. During this violent process, heavy elements are created through nuclear fusion and scattered throughout space, providing the building blocks for new stars, planets, and eventually life. What remains after a supernova depends on the star's initial mass. Lower mass stars leave behind white dwarfs, dense, Earth-sized remnants composed mainly of carbon and oxygen. Stars between about 10 and 25 solar masses create neutron stars, incredibly dense objects where electrons and protons are compressed together into neutrons. The most massive stars collapse into black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape once it passes the event horizon. This cosmic recycling process continues as the elements released from dying stars contribute to the formation of new stars and planetary systems. Stars are born from nebulae, live their lives fusing elements, and then die, returning their material to space to form new nebulae. This cosmic cycle has been ongoing for billions of years. Through this stellar recycling process, we are quite literally made of stardust. The elements in our bodies were forged in the hearts of stars that lived and died billions of years ago. The diverse life cycles of stars are fundamental to understanding our cosmic origins and the formation of everything we see in the universe. The moon has a layered structure similar to Earth, but with several key differences. At its center is a small solid iron core surrounded by a partially molten layer. This is covered by a solid mantle and finally a crust. The lunar crust is not uniform in thickness. It's thicker on the far side at approximately 100 kilometers, while on the near side, the crust is only about 60 kilometers thick. The moon's surface features two main regions, the darker maria, which are ancient lava flows, and the lighter highlands, composed mainly of anorthosite. Unlike Earth, the moon has no atmosphere or magnetic field. This is why the moon is covered in impact craters that haven't eroded over billions of years. The moon's surface is covered in regolith, a fine dust layer. This regolith is continuously formed by micrometeorite impacts pulverizing the lunar surface. These unique characteristics of the moon's structure and composition have been preserved for billions of years, providing valuable insights into the early solar system. Stars and moons, though vastly different in scale, are deeply interconnected in our cosmos. Stars are massive nuclear furnaces, while moons are relatively small rocky bodies, yet they're linked through materials and gravity. One of the most fundamental connections is that stars produce the heavy elements necessary for rocky bodies like moons to form. Inside stars, nuclear fusion transforms simple hydrogen into progressively heavier elements like carbon, oxygen, silicon, and eventually iron. These heavier elements are essential building blocks for rocky moons and planets, distributed through space via stellar winds and supernovae. In our own solar system, the sun's gravitational influence was crucial in shaping the environment where planets and moons could form. About 4.6 billion years ago, a cloud of gas and dust collapsed to form our sun at the center, surrounded by a spinning protoplanetary disk. From this disk, planets formed through accretion, gathering materials at different distances from the sun. Similarly, moons formed around the planets. While stars form directly from the collapse of nebulae, moons typically form through different mechanisms. Regular moons form through accretion in orbit around planets, similar to how planets form around stars, but on a smaller scale. Irregular moons, however, are often captured objects that passed too close to a planet's gravitational field and became trapped in orbit. Some moons in our solar system are particularly interesting because they may harbor environments suitable for life. Europa, one of Jupiter's moons, and Enceladus, one of Saturn's moons, are believed to have subsurface oceans of liquid water beneath their icy crusts. These hidden oceans are kept liquid by tidal heating, a process where the gravitational pull of their parent planets creates friction and heat within the moons. This makes these moons some of the most promising places to search for extraterrestrial life in our solar system, highlighting the fascinating connection between stars, planets, and their moons. The interconnection between stars and moons shows us how different scales of cosmic objects work together to create potentially habitable environments throughout the universe.